Welcome to our lab for our O2 and our air fuel sensors. Today we'll be talking about oxygen sensors. Right now we're doing the wideband, but on this vehicle there is also an air fuel ratio sensor. That is the first sensor. It is before the catalytic converter. Our second sensor after the CAT is a wideband sensor, and it is a pretty big difference on our readings. Oxygen sensors work based on our ions that are in oxygen, and they attract from inside the CAT onto our little planar or thimble, depending on your sensor, and they either produce a current or create resistance in the actual sensor. And whenever they produce the voltage, they produce it in voltage. And our second one here, it is a wideband or a inert cell, and was invented by some smart dude way back when. Now there are two different types. You have a critical current and ion pump. We have a critical current. We know this because it is a 4-wire, not a 5-wire. A 4-wire calculates based on amps, and ion has a pump circuit, and we do not have a pump circuit. Go. Another advantage of wideband sensors is that they are far more accurate about reading how lean or how rich you are. Wideband sensors can go all the way down from 10.1 all the way up to 23.1, or not 0.1, but 2:1 ratio on our oxygen to fuel, and otherwise known as stoichiometry. Stoichiometry is just our percentage of oxygen in the air to fuel that's being burned off. And our oxygen sensor takes our amount of oxygen in the exhaust, and it assumes what would be the amount of fuel going into the engine being burned and leaving a little bit of oxygen behind. And a perfect stoichiometric ratio would be 14.7 to 1. That's how many parts of air, oxygen, air can be in 1 unit of fuel. You always want to try and keep it within 14.7. Another advantage of our wideband being wideband is our little graphs up here. They're far more accurate. Switching sensors, which is our other one up here. Switching sensors, they will be down and up, either on or off. But our wideband sensors will give us a far more accurate reading. This is why we use them. Typical switching sensors are either zirconium or titania. And zirconium, it'll look something like this. This is a better representation of our ceramic zirconium dioxide outside of our oxygen. Outside air comes in here. This is our inner electrode, outer electrode. Ions will attract to this. Other ions, oppositely charged ions, will attract to the inside. Oppositely will attract to the outside. And yeah, it looks something like this. Our outside air will come in through here, and oppositely charged ions will attract. Another thing about wideband is much hotter than our switching, just because that's how it runs. It runs better that way. Our switching sensors run about 600 to 1,000 degrees Fahrenheit. Our zirconiums are 600 to 800. Our titania is about 1,200. And our wideband is about 1,300 degrees for running best. This is our air fuel sensor, and this is our heated exhaust. This one is our switching sensor. This one is our wideband sensor. And as you can see, whenever we rev it up, it shoots up. This one shoots down. This is good. It means that they're behaving fairly. Whenever we accelerate, they're getting rich, and whenever we decelerate, they're getting lean. All right, and let's go show you what happens when we create a vacuum leak. So for our vacuum leak portion of this lab, we're gonna be looking at this blue line in particular, our air-fuel ratio sensor. And once we create this vacuum leak, we should see a drop. It should lean out, so you have more air going in than what's expected. It's going in after the MAF sensor, where our engine reads the amount of air coming in. So once we create this leak, should shoot up, lean out. Now the engine is counted for the amount of air. Now it's not too happy, as you can see, but if we plug it back in, it's happy again. It's going to readjust to where it was. All is well in the world.